Good morning. So, in the last video, we have studied the introduction to this chapter on circuit theorems. We have studied the Ohm's law and some important terms called as terminologies that are being most commonly used while dealing with the network analysis or circuit analysis. So today we are going to study the Kirchhoff's laws, which you have already studied earlier. There are two laws proposed by Kirchhoff's in order to analyze the networks or circuits. Analyzing a network means that we have to find out the currents flowing through the different branches of that network or the potential difference across a certain branch of the given network. So finding out these unknown quantities is called as the network analysis. To analyze the given network, here we are going to study the two most important laws that are being commonly used. The first one is the Kirchhoff's current law and the second one is Kirchhoff's voltage law. A single law is unable to analyze the given complicated networks. We have seen that if the given network is simple one, a series circuit, then it can be analyzed by using the Ohm's law itself. But if the given network is little complicated, then only Ohm's law is not sufficient in order to find out the currents flowing through the different branches of that network. So for that purpose, we have to make use of these Kirchhoff's laws. So out of these two laws that we are going to use in order to analyze the network, let us study these laws one by one. So let us see first what is the Kirchhoff's current law. This Kirchhoff's current law is applied to a junction in the given network. Usually the Kirchhoff's current law is applied to a junction in the given network. Suppose we have this junction P in the given network, and at this junction P there are various branches of that network arriving at this point P or at the junction P. Suppose this first branch carries the current I1 towards the junction P. The second branch I2, carries the current I2 away from the junction P. The third branch carries the current I3 towards the junction P. The fourth branch carries the current I4 away from the junction P, and the fifth branch carries the current I5 towards the junction P. So at this point P, the 5 different branches of that network are arriving, and through these different branches the different currents are flowing such that some of the currents are approaching to the junction P and some of the currents are leaving away from the junction P. So when we want to apply this Kirchhoff's current law to this junction P of this network, let us see first what is this Kirchhoff's current law. So at any junction in the given network, it is observed that the algebraic sum of the currents is always equal to 0. The algebraic sum of the currents at any junction is always equal to 0. What does it mean? It means that whatever the current that arrives at a point or at a junction in the given network, same amount of current leaves away from that junction. neither the current is generated at the junction P nor the current is dissipated at the junction P. So whatever the current arrives at the junction P, all that current leaves through other branches away from the junction P. So that is the meaning of this Kirchhoff's current law. The algebraic sum of the currents at any junction is equal to 0. So if we observe here, the currents I1, I2, I3, I4, I5 are flowing through the different branches arriving at the junction P. So in order that the algebraic sum of the currents at the junction P to be equal to 0, we have to show this, we have to make a certain sign convention. The usually adopted sign convention is that the currents that are approaching to the junction P are treated to be positive and the currents that are leaving away from the junction P are treated to be negative. So listen to this sign convention once again. The currents that are approaching to the junction P are considered to be positive and the currents leaving away from the junction P are considered to be negative. So if we apply this sign convention, what we can say here is that since the current I1 is flowing towards the junction P, the current I1 must be treated as positive. The current I2 is leaving away from the junction P, the current I2 should be treated as negative. The current I3 is flowing through this third branch towards the junction P, so it must be treated as positive. The current I4 flowing through the fourth branch is leaving away from the junction P, so it must be considered to be negative. And through the fifth branch, the current I5 is flowing towards the junction P, so the current I5 must be considered to be positive. So, in accordance with this statement of the Kirchhoff's current law, we can express this as I1 plus I2 plus I3 plus I4 plus I5 is equal to 0. While expressing this relation, we have not taken into consideration the sign convention. Now, if we take into consideration the sign convention that the currents approaching to the junction are to be treated positive and the currents leaving away from the junction P are to be considered negative. So here we can consider this is plus I1. I2 is leaving from the junction P, so should be treated negative. So it is minus I2 plus I3 is approaching to the junction P, so it is positive, plus I4 is leaving away from the junction P, so should be considered as negative. So it is minus I4 plus I5 is approaching to the junction P, so should be considered as positive. So this must be equal to 0. So by taking into consideration the sign convention, we can express the same relation like this. So this can be expressed as I1 plus I3 plus I5 is equal to I2 plus I4. What is the left hand side of this relation? The left hand side of this relation is the total current approaching to the junction P. And this is equal to the right hand side of this relation represent the total current leaving from the junction P. So this is the total current approaching to the junction P is equal to the total current leaving away from the junction P. and that is nothing but the Kirchhoff's current law. So, for a given network, we can apply this Kirchhoff's current law to each and every junction. Each and every junction. So, this is the Kirchhoff's current law. So, next we'll discuss the Kirchhoff's voltage law. So, this is nothing but the algebraic sum of the currents at any junction is equal to 0, and that is the statement of Kirchhoff's current law. So, in accordance with this relation, we can state that the algebraic sum of the currents at any junction is equal to 0. So, that is about the Kirchhoff's current law. And next, see the Kirchhoff's voltage law. This Kirchhoff's voltage law is to be applied to a closed loop. The Kirchhoff's voltage law is applied to a closed loop in the given network. How does it state? Let us see. This Kirchhoff's voltage law states that the algebraic sum of the voltages around any closed loop or any closed path or any closed mesh of a given circuit is equal to 0. The algebraic sum of the voltages around any closed path or any closed circuit or any closed loop is equal to 0. Or it also can be stated as the algebraic sum of all the applied EMFs and the products of the currents and the resistances in different branches of that loop is equal to 0. So, we can mathematically express this Kirchhoff's voltage law as summation E plus summation IR is equal to 0. This summation E represents the algebraic sum of the EMFs that appears in the given loop, and summation IR represents the sum of the products of the currents and the resistances in the different branches of that closed loop. And the summation E plus summation IR is always equal to 0. So that is the Kirchhoff's voltage law. While applying this Kirchhoff's voltage law to a closed loop, we have to make a certain sign convention. Now, before we see what is this sign convention, let us consider we have a closed loop like this. Suppose this is the source of EMF E1, this is the source of EMF E2, this is the resistance R1, This is the resistance R2, this is the resistance R3, and this is the resistance R4. So let us consider we have this closed loop A, B, C, D. Now, it is not that we have only this much given network, but as well there are certain branches bifurcating from these points A, B, C, D, so that whatever the current is sent by the source E1, it is not that all that current flow through R4 or R3, or whatever the current is sent by the source E2, all that current flows through R2 and R3. But certain current branches in these branches also, whatever it is, whether this direction of the current is this direction or this direction, we do not know. All that depends on what are the values of E1 and E2, and also it depends on what is the rest of the network. So let us consider, for the sake of understanding or for the sake of simplicity, that the current I1 originate from the source E1, and as we know well that always the conventional current flow from the positive terminal of the battery to the negative terminal in the external circuit. So this current I1 will be sent by the source E1 in this direction. Similarly, this source E2 will send the current I2 in this direction. This is the current I2 sent by the source E2. So through this resistance R1, the current I1 will flow. The current I1 will flow through the resistance R1. Through the resistance R2, the current I2 will flow. It is not that all that current I2 will flow through R3, or this current I1 will flow through R3, but it depends on what is the rest of the network and certain current branches from this junction C, so that the current flowing through R3 is not equal to I2 or is not equal to I1, but it is something different, and let us consider this current is I3. And whatever the current I3 arrives at the junction D, all that current may not flow through R4, or this current I1 may not flow through R4, but part of the current will branch through this junction A in this branch or in this branch. So the current flowing through R4 is C equal to I4. Say I4 is the current flowing through this resistance R4. Now we want to find out the values of these currents I1, I2, I3, I4 flowing through these different branches of this given network. Here A, B, C, D is the closed loop or a mesh, and we want to apply the Kirchhoff's voltage law to this closed loop. So whenever we want to apply the Kirchhoff's voltage law to the given loop, first we have to decide the direction in which we are going to trace the given network. Either we can trace this network in the direction from A to B, B to C, C to D, and D to A back again, or else we can as well follow the path starting from point A to D, D to C, C to B, and B to A back, so that if the starting point and the end point, after traversing the different branches of that network, if we arrive at the same starting point, the path followed is said to constitute a closed loop or a mesh. So we can apply this Kirchhoff's voltage law to any such closed network, every such closed network or closed loop in the given network. So let us first decide the direction in which this loop is to be followed or traced. So let us consider that we want to follow this path A, B, C, D, A. This is a closed loop A, B, C, D, A. And we want to apply this Kirchhoff's voltage law to this closed loop. So before we apply the Kirchhoff's voltage law to this closed loop A, B, C, D, A, let us try to make certain conventions. What conventions we need to make here? The first convention is regarding the EMF of the source. Whether we should consider the EMF of the source E1 as positive or negative, or whether we should consider the EMF of the source E2 as positive or negative. So that we have to decide first. Again, we have to decide about the potential difference produced across these resistors R1, R2, R3, R4 when the currents I1, I2, I3, I4 flows through these resistors respectively. Certain potential drops will be developed, and whether this potential drop should be considered as positive or negative, for that purpose we want to make another convention. The first convention regarding the polarity of the source of EMF made here is that when we are traversing the loop in this sense, in this direction, if we traverse a source of EMF in the direction of increasing EMF, then the EMF of that source should be considered as positive. And if we are traversing that particular branch of the network in the direction of decreasing EMF, then the EMF of such source should be taken as negative. So if we use this sign convention here, while traversing this branch from A to B, we have the source of EMF E1 in the path, and while traversing in this direction, we are moving from the positive terminal of the source to the negative terminal, and as we know well that the potential of the positive terminal is higher and that at the negative terminal of the battery is lower, so we are traversing in the decreasing direction of the potential. We are traversing in the decreasing direction of the potential. So the EMF of the source E1 must be considered as negative. If we consider the second source of EMF in the branch BC, here we are traversing this source from the negative terminal towards positive terminal. When we are traversing this branch BC, we are traveling from the negative terminal of the source to the positive terminal, so that we are traversing in the direction of increasing potential. And when we are traversing in such increasing direction of the potential, the EMF of the source should be considered as positive. So in accordance with this sign convention, the EMF of the source E1 should be negative and the EMF of the source E2 must be taken positive if we are traversing this loop in this direction. Then the current I1 is flowing through this resistance R1 from B towards A, that is in the direction of, in the opposite direction to that of the traverse of the loop. The current I1 is flowing in the direction opposite to the direction of traverse of the loop. So that the product I1R1, when we are traversing this loop in this sense or from A to B, we are traversing in the increasing direction of potential. Why? Because as we know well that the current always flow from a point at higher potential to a point at lower potential. Since through this resistance R1, the current I1 is flowing from B towards A, so this current must be flowing from a point at higher potential to a point at lower potential, so that the potential drop across the resistance R1, that is I1 R1, must be treated as positive because we are traversing in the direction of increasing potential. Similarly, the potential drop across this resistance R2, that is I2 R2, will be should be taken as negative because here this branch of the loop is to be traversed in the direction of current flowing through this resistance R2, so that as we know that the current always flow from a point at higher potential to a point at lower potential. So while traversing this branch, we are traversing in the direction of decreasing potential, so that the product I2 R2 must be taken negative. Then through this branch CD, we have a resistance R3 through which the current I3 is flowing. The potential drop across R3 will be I3 R3, and while traversing this branch, again we are traversing in the direction of decreasing potential itself, so that the product I3 R3 must be taken negative. And through this branch DA, we have a resistance R4 through which the current I4 is flowing, so that this branch, since is traversed in the direction of decreasing potential, the product I4 R4 also must be treated as negative. So we can write the voltage equation for this closed loop A B C D A. So what we'll get? In first we have the source of EMF E1, and while traversing this loop from A to B, we are moving in the direction of decreasing potential, so that the EMF of the source E1 must be taken negative. So it is minus E1. Then we have the resistance R1 through which the current I1 is flowing, so that the product I1 R1 will be positive here because we are traversing this branch in the direction opposite. The current flowing through this branch is in the direction opposite to the direction of traverse of the loop. So this product I1 R1 must be treated positive. Then the next branch contains the source of EMF E2. Here this source of EMF E2 is to be traversed from negative terminal to the positive terminal, that is in the direction of increasing potential. So the EMF of this source must be taken positive. So it is plus E2. Then the next we have the resistance R2 through which the current I2 is flowing. So the potential drop across R2, that is I2 R2, should be taken negative here because we are traversing this branch in the direction of current flowing through it. So that that is nothing but in the direction of decreasing potential. So this potential drop I2 R2 must be taken negative. So it is minus I2 R2. Then the next branch contains the resistance R3 through which the current I3 is flowing, and this branch is traversed in the direction of current flowing through it. So this product I3 R3 also must be taken negative. It is minus I3 R3. And the last branch DA contains the resistance R4 through which the current I4 is flowing. The product I4 R4 again must be taken negative. So it is minus I4 R4, and this must be equal to 0. So the sum of all these potentials must be equal to 0. That is in accordance with the Kirchhoff's voltage law. So we can express this relation as E2 minus E1 is equal to, if we transfer these terms to the right hand side, we can express it as I2 R2 plus I3 R3 plus I4 R4 minus I1 R1. So summation E is equal to summation IR. So this is nothing but summation E is equal to summation IR, or this is nothing but summation E plus summation IR is equal to 0. So that is how we can write the voltage equation for each and every closed loop existing in the given network, right? So that is about the Kirchhoff's voltage law. That is about the Kirchhoff's voltage law. So using this voltage law, how can we analyze the given network? So the analysis of the given network, to clarify it or to make the concept of analyzing a network by using the Kirchhoff's law, let us consider one example. So that is about the voltage law. And let us consider, if we consider this example, then the concept of this Kirchhoff's voltage law and the Kirchhoff's current law will be more clear to you. So let us see one example. We are given a network that contains 3 resistors R1, R2 and R3, and the 2 sources of EMFs E1 and E2. So this is the resistor R1, this is the resistance R2, this is the resistance R3, this is the source of EMF E1 of value 25 volt, this is the source of EMF E2 having the voltage 20 volts. The resistance R1 is given to be 5 ohm, R2 is given to be 10 ohm and R3 is given to be 15 ohm. So this is the junction A, B, C, D, E, F and A. So we have this network, and let us consider the current I1 is sent by the source E1, the current I2 is sent by the source E2 in the circuit. When both these currents arrive at the junction B, the total current flowing through R3 is I1 plus I2. Say this current is I3. This current is I3. I3 is nothing but equal to I1 plus I2. So we are asked to find out the currents I1, I2, I3 and the potential drops across the resistors R1, R2 and R3. So if by some means we can find out the currents flowing through these different branches of this network and the potential drops across the different branches of this network, that is nothing but the analyzing a given network. So this can be done by using the Kirchhoff's laws. First is the Kirchhoff's current law and the second one is Kirchhoff's voltage law. So if we first apply the Kirchhoff's current law to the junction B, if we apply the Kirchhoff's current law to the junction B, here what we observe is that the current I1 is approaching to the junction B, the current I2 is approaching to the junction B and the current I3 is leaving away from the junction B, so that we can write I1 plus I2 is equal to I3, or we can express it as I1 plus I2 plus minus I3 is equal to 0. So that summation R is equal to 0 at the junction B. Similarly, at junction E also we can write the same thing. Other way around. It should be other way around. Here, for junction E, the current I3 is approaching to the junction E, and the currents I1 and I2 are leaving away from the junction E, so that I3 must be taken positive here, I1 and I2 must be taken negative here. So depending on to which junction we apply the given Kirchhoff's current law, we have to decide the sign convention, right? So in that case, we should again the relation is same, I1 plus I2 is equal to I3, but the only difference is in the sign convention. Minus I3 will be equal to I1 plus I2 in that case. Okay. Minus I3 plus I1 plus I2 is equal to 0, or I3 is equal to I1 plus I2. So Kirchhoff's, that is the Kirchhoff's current law if we apply to the junction B and to the junction E. Then apply the Kirchhoff's voltage law. By applying the Kirchhoff's voltage law to the different loops, we will get the different voltage equations. And solving these voltage equations simultaneously, we can find out the currents flowing through the different branches of this loop, or we can find out the potential drops across the different branches of that loop. So, since we can apply the Kirchhoff's voltage law to a closed loop, in this network there exist three different closed loops. The first closed loop here is A, B, E, F, A. A, B, E, F, A. This is the first closed loop. The second closed loop is B, C, D, E, B. B, C, D, E, B. This is the second closed loop. And the third closed loop is A, B, C, D, E, F, A. A, B, C, D, E, F, A. So there are three different closed loops in this network. So we can apply the Kirchhoff's voltage law to each and every closed loop in the given network, and we can write the voltage equations, and from these voltage equations, by solving these voltage equations simultaneously, we can obtain the currents flowing through the different branches of this loop network and the potential drops across the different branches of this network, and that is nothing but the analyzing a given network. So let us write the voltage equation for the first loop A, B, E, F, A. So if we consider this first closed loop A, B, E, F, A, the first branch AB contains the resistance R1 through which the current I1 is flowing in the direction of traverse of the loop. So the product I1 R1 must be treated as negative because we are traversing this branch in the decreasing direction of potential. So it is minus. Then through the resistance R3, the current I3 is flowing again in the direction of traverse of the loop. So the product I3 R3 must be taken negative. Then the branch EF does not contain either the source of EMF or the resistance. So no potential drop is developed across E and F, or this branch EF. Then the branch FA contains the source of EMF E1, and while traversing this branch from F to A, we are moving from the negative terminal of the source to the positive terminal of the source. So in the direction of increasing potential, so that the EMF of this source must be taken positive. So this must be equal to 0. So this is the voltage equation for the first closed loop. Now using the values of R1, R2 and E1 here, we can express this relation as E1 is 25. This is I1. R1 is 5 ohm. So it is 5 R1 plus 15 I3 is equal to E1 is 24. So we have transferred this term to the right hand side so that the signs of all the terms are changed. So it is 5 R1 plus 15 I3 is equal to 25. Or since in accordance with the Kirchhoff's current law, we have I3 is equal to I1 plus I2. Using I3 is equal to I1 plus I2 here, we can express this relation as 5 R1 plus 15 into bracket I1 plus I2 is equal to 25. So if we open up this bracket, this should be I1 here. Should be I1 here, not R1. Should be 5 I1. R1 is 5 ohm, so it is 5 I1 plus 15 I3 is equal to 25, or 5 I1 plus 15 into bracket I1 plus I2 is equal to 25. So if we open up this bracket, 5 I1 plus 15 I1 is 20 I1 plus 15 I2 is equal to 25. Dividing both sides of this relation by 5, we will get the relation. By dividing by 5, we get 4 I1 plus 3 I2 is equal to 5. So this is the simplified voltage equation for the first closed loop A, B, E, F, A. So this is equation 1. Then we'll apply the Kirchhoff's voltage law to the second closed loop here. That is the loop B, C, D, E, B. B, C, D, E, B. So the second closed loop here. So through this in the first branch BC contains the resistance R2 through which the current I2 is flowing in the direction opposite to the direction of traverse of the loop, so that we are traversing the loop or that branch in the direction of increasing potential. So the product I2 R2 must be taken positive. The third branch, second branch CD contains the source of EMF E2, and while traversing this branch, we are moving from the positive terminal of the battery to the negative terminal, that is in the direction of decreasing potential. So the EMF of this source must be taken negative. Then the branch DE does not contain either a source of EMF or the resistor, and the branch EB contains the resistance R3 through which the current I3 is flowing in the direction opposite to the direction of traverse of the loop. So this EMF I3 R3 must be taken positive, and this must be equal to 0. So this is the voltage equation for the second loop in this network. So using the values of R2, R3 and E2 here, we can write R2 is 10 ohm, so it is 10 I2. Transferring this E2 to the right hand side, we can express this as R3 is 15 into I3 is equal to E2 is 20 volt. So again, substituting I3 as I1 plus I2, we get 10 I2 plus 15 into bracket I1 plus I2 is equal to 20. If we open up this bracket, we can express it as 15 I1 plus 15 I2 plus 10 I2 is 25 I2 is equal to 20. So again, dividing by 5 on both sides of this relation, we get 3 I1 plus 5 I2 is equal to 4. So this is equation 2. This is the simplified voltage equation for the second loop. And now by solving these two equations simultaneously, we can find out the values of I1, I2, I3 and the potential drops across the resistors R1, R2 and R3. So if we can find out the values of I1, I2, I3 and the potential drops across R1, R2 and R3, we can say that we have analyzed the given network. So let us solve these two voltage equations simultaneously. To solve these two equations simultaneously, we can eliminate first either the value of I1 or we can eliminate I2 from this equation. If we eliminate I1, we will get the value of I2. If we eliminate I2, we will get the value of I1. We can do it either way around. So let us see, let us eliminate I1 first. When we want to eliminate I1 from these two equations, what we need to do is we have to multiply equation 1 by 3, equation 2 by 4 and take the subtraction of the two. So equation 1 multiplied by 3 minus equation 2 multiplied by 4. Equation 1 multiplied by 3 is 12I1 plus 9I2 is equal to 15 and equation 2 multiplied by 4 is 12I1 4 plus 20I2 is equal to 16. So multiplying equation 1 will get this equation, multiplying equation 2 we get this equation, and now if we take the subtraction of these two equations, we will get plus 12I minus 12I will cancel, plus 9I2 and minus 20I2 is nothing but minus 11I2 is equal to plus 15 minus 16 is minus 1. Therefore, I2 is equal to 1 upon 11. So minus minus will become plus and I2 will be equal to 1 by 11. So once we get the value of I2 here, using this value of I2 in either of these two equations, we can find out the value of I1. So let us substitute the value of I2 in equation 1. So we get 4I1 plus 3 into bracket I2 is 1 by 11 is equal to 5. So 4I1 is equal to 5 by 1 minus 3 by 11. So LCM will be 11. So this is 55 minus 3. So this is 52 upon 11. So I1 is equal to 52 by 11 into 1 by 4. So this is equal to 13 by 11. That's your problem. So I1 is equal to 13 by 11, I2 is equal to 1 by 11. And knowing the values of I1 and I2, easily we can find out the value of I3 because I3 is equal to I1 plus I2. So we have I1 equal to 13 by 11 ampere, I2 equal to 1 by 11 ampere. Therefore, I3 is equal to, since I1 plus I2, so it works out to be equal to 13 by 11 plus 1 by 11. So this is 14 by 11 ampere. So we have found out the currents I1, I2 and I3 flowing through these three resistors R1, R2 and R3. So I1 is 13 by 11 ampere, I2 is 1 by 11 ampere and I3 is 14 by 11 ampere. So these are the currents I1, I2 and I3. And knowing the currents I1, I2 and I3, now we can find out the potential drops across R1, R2 and R3. Therefore, PD across R1 is nothing but I1 R1. Is nothing but I1 R1. So I1 is 13 by 11 multiplied by R1 is 5. So potential drop works out to be equal to 65 by 11 volt. Potential drop across R1 works out to be 65 by 11 volt. Similarly, we can find out PD across R2, that is nothing but I2 R2. I2 is 1 by 11 multiplied by R2 is 10 ohm. So this is equal to 10 by 11 volt. And PD across R3 is nothing but equal to I3 R3. I3 is 14 by 11 ampere multiplied by R3 is 15 ohm. So this is equal to कितने है 160 is 210 divided by 11 volt. So these are the potential drops across the resistors R1, R2 and I3. So we have found out the values of I1, I2, I3 as well as the potential drops across the resistors R1, R2 and R3. And this achieving these values is nothing but the analyzing a given network. So by using the Kirchhoff's laws, we can analyze any complicated network. But application of these Kirchhoff's laws to analyze the complicated network is a tedious process. We have to write down the voltage equations for each and every closed loop and solve these voltage equations simultaneously to obtain the currents through the different branches. And knowing the currents and the resistors in the different branches, we can find out the potential drops across the different resistors or different branches of that network. So this is a little tedious process, a time consuming process. So in short, we can analyze such complicated networks by using the other laws that we are going to study next, the Thevenin theorem, Norton theorem and the superposition theorem. So before we discuss these theorems, we want to study some more concepts that will continue in the next video. Okay, thank you.